All right, so today we're continuing our journey, kind of exploring the different types of potential energy. Sorry about that. Today we're going to be looking at elastic potential energy, the potential energy an object has from being stretched or compressed. This equation should look really, really familiar. If you remember, kinetic energy is 1/2 mass times velocity squared. In this case, we're working with the exact same. It looks the exact same. For the To calculate the potential energy of an elastic object, we're taking 1/2 times its k, which we've seen before. That would be our spring constant. That typically has a unit. That's what I'm looking for, newtons per meter. Essentially, for every meter I stretch or compress a spring, how much force is it exerting? X squared, that would be our change in length. I'm going to put that in parentheses. Really, our change in length is going to be measured in meters as well, but just remember we have to square those meters. All right, so first thing I like to do is prove that we are still working with the energies we've been working with. So for work, we found that joules are equal to kilograms meter squared per, uh, what's the word I'm looking for here? Second squared, duh. Um, so really, that's the unit we're working with, kilogram meter squared per second squared. So in this case, I have newtons per meter times, we're going to square these meters here, times meter squared. So I should probably figure out what a newton is. So a newton is a kilogram meters per second squared because it's mass times acceleration. So we have that over meters times meters squared. All right, bear with me for a little bit. That meters is going to cancel out the squared part of it. So now I have kilogram meters per second squared times meters. Meters times meters is meter squared. So I end up with kilogram meter squared per second squared. These two things are the exact same thing. Elastic potential energy using this formula gets us to the exact same unit that what a joule actually is. So let's actually do a little bit of work with this. So let's say I'm really interested in a pinball machine and I want to know the elastic potential energy for a spring uh, where the elastic potential is, let's say the elastic potential for this spring is 10 newtons per meter. And let's say that we're going to stretch it 10 centimeters, or if I got to convert that to meters, let's say we're going to move that 0.1 meters. Okay, I want to calculate the elastic potential energy for that. So in this case, 10 times 0.1 is 1. Keep my meters cancel out, so that's 1 newton. Um, and then times 1/2. So that'll get me 0.5 joules of elastic potential energy. Ignore that part. 0.1. Let's get out a calculator just to double check. All right, bring this guy over. So I have point. Oh, you know what I did wrong there? I did that wrong. Because it's not times 0.1. We got our spring constant. It's our distance squared. All right, so I'm going to take 0.1 times 0.1. That takes care of my 0.1 squared. Times 10 times 1/2 or 0.5. Really, what my potential energy is 0.05 joules. That makes way more sense. That spring constant tends to be, that's kind of on the low side. 10 newtons for every meter. That's not a whole lot of force there. Granted, and we're not even moving it all that much. So squaring it, gets us to a smaller number. And that makes sense. Um, Essentially, this equation is still pretty basic algebra. If you can use the kinetic energy equation, you're going to be fine for this as well. Where it gets really interesting for things like mechanical engineering or even like do-it-yourself pinball machines is if you know how much potential energy you need and you know just how much you can stretch or compress a spring, it allows you to figure out what does your spring constant need to be, which would affect which ones you buy for your pinball table or machine or anything like that. All right, that's elastic potential energy. Pretty short, pretty sweet. Good luck.